Hi, so welcome to the second class on martingales. So in the beginning we saw an introduction to martingales, then we understood a bit how martingales connect with convexity of functions and monotonicity of them as well. And then we looked into integrals of martingales in the discrete sense and how this can be interpreted as betting systems. Today we're going to talk about uh, a famous inequality called the Upcrossing inequality or uh, the Upcrossing estimate. So this in principle is a technical statement, but soon you'll see that this is not only very intuitive, but interesting and useful. So we start as usual with a martingale. So we have this martingale here, and let us think for a moment that this martingale represents some stock price or something that we can understand as money or some profit making function. So we start with a certain value here, and then as time goes by, the value can go up or down in perhaps an unpredictable way. Okay, and we talk about the possible strategy to make money out of this martingale. So we know that we have one unit of this martingale in the beginning, but we could sell and buy this through some function h, some process hn, which is interpreted as our betting scheme, and it's a predictable process. So there are several possible strategies that we can implement with h, and we have seen in the last class that no matter what strategy you use to buy and sell, you always stay a martingale. If you start a martingale, you stay a martingale. So there is not much to be gained there. But this will turn into our advantage. So the fact that we can never make something that is not a martingale means that different strategies give us different theorems. For every strategy H, we get a new martingale and we can extract information from that martingale. And the martingale that we are going to study today is a very intuitive one. So if this function is oscillating like it shows in the picture, let us try to make some profit here by declaring that below this curve A here, so at some value A, we decide that this price is too low, so time to buy. And maybe if it crosses some other threshold, B, we're going to say, okay, now it's too expensive, time to sell. So this strategy is well known in people who invest in finance. It's just a simple buy low, buy low and sell high. Okay, sounds intelligent, right? If you're buying for a low price and selling for a high price, you're making a profit. But we know it cannot be something that gives you money because it's still a martingale. So let's see what kind of result this strategy gives us. So this is going to be our first buying time, right? This is going to be buy 0. And then at a later point, the price is going to oscillate, and if when it reaches this point here, it's too expensive and we should sell. So this is sell 0. But then the price evolves. It goes back to a low plateau here. So it's time to buy again. This is buy 1. And oscillates until the first time it crosses again. And this is sell 1. and so on and so forth, right? We do this forever. Now we need a way to express this in a rigorous form, right? What are these times, b0, s0, b1, s1? And what is the function h that we're trying to describe? So b0 is going to be simply -1. So we always, like if we imagine that we bought this martingale before it even starts. Okay. And now we define b1 as the first time the infimum in n such that the martingale is smaller or equal to, sorry, bigger or equal to, bigger or equal to b. So it's our first, oh, sorry, that's why I'm confused here. This is the first selling time. So we sell, sell 0 is the first time when the price is above b. Okay, now we have to define b1. b1 is also going to be the first time for which, but now it's important to observe that here it's not 0 anymore. It's the first time after we sold the last time, such that the price is again smaller or equal to a. Right? So as you can see in this picture, at S0 we are bigger or equal to b, but the first time after S0 that we are below a is b1. Now what's b2? Sorry, what's S1? S1 is the first time after b1 such that xn is again above b. And we can define inductively bn and sn for every n. Now we have everything set up to define our strategy h. So we're trying to define, sorry, hn here. It's going to be a predictable process later. So h, intuitively speaking, is going to be we are in or out. We are buying all of x or known of x, and we buy when bi is strictly smaller than n, smaller or equal than some si for some I. And 0 otherwise. So imagine that here we have a plot of the times that we saw above. B0 is always here. Then we sell. Then we buy again. And so on. So H is going to be 1 here between we buy and we sell. You see? Then it's 0. Then it's again 1 until the next time we sell. So this purple region is H equals 1. So let us see that H is in fact a predictable process. So what does it mean for H to be predictable? It means that for every n, Hn belongs to, perhaps for every n bigger than 1, Hn belongs to Fn minus 1, which is a stronger requirement than being adapted. So remember that Fn is something that we didn't mention yet, but it always has to be there just for the definition of a martingale. When we said that xn is a martingale, we have already a filtration, Fn, and it's adapted to Fn, but Hn is more than adapted. It's actually predictable. So how do we show that it's predictable? So let us look at the event at Hn, right? If we want to show that Hn is measurable with respect to something, we can look at this event. If Hn equals 1 is an Fn minus 1 measurable event, then H is Fn minus 1 measurable because it can only assume this value or 0 in the complement of this event. So that's all we have to prove. So let's break down this event further. So this means that there exists some I, natural number, such that first of all, BI has to be smaller than n. So I write this event here. And moreover, Si has to be bigger or equal than n. So event Si bigger or equal than n. So this is all we have to prove, that this is Fn minus 1 measurable. And the way we do this is showing that everything that is involved here is Fn minus 1 measurable. So this in the end is going to be only a union and an intersection, unions and intersections of Fn minus 1 events. So first let's take a look at Bi. So, first let's take a look at B0. Actually, B0 is minus 1. So it's a deterministic thing. And Bi is always smaller than n for every natural n. So this is always Fn minus 1 measurable. But I want to go further. I want to say that this is a stopping time. We saw this already, right? And S0, if you remember, let's look back into the definition of S0. S0 is the first time that xn is bigger or equal to b. So S0 is a heating time. Therefore, it's a stopping time. Great. So I'm not going to give the full proof here, but the same way as we proved that every heating time is a stopping time, we can see that these heating times that happen after a stopping time are also stopping times. So prove, this is an exercise, prove that Si and Bi are stopping times for every I. Actually, more generally, if you have a heating time, so the first time that the process enters a set, but after another stopping time, then this is also stopping time. It's like a chained heating time. So you can prove this, and in particular, you get by induction that all these are stopping times. So now we have that as I's and Bi's are stopping times, and we can get back to what we want to show, right? Let's copy this. This is what we want to show is a stopping time, is in Fn minus 1. Okay, so by parts, Bi is a stopping time. So Bi smaller than n is exactly Bi smaller or equal than n minus 1, because these are integer valued random variables. And this, by the fact that Bi is a stopping time, is in Fn minus 1. Great. So very similarly, if you look at Si, this is the complement of Si smaller than n, right? If it's bigger or equal, it's because it's not smaller. And this, by the same argument as above, is Si smaller or equal than n minus 1 complement, so it's also here. And since this is for every I, we've proved that this h n equals 1 is fn minus 1 measurable, and we're good to go. So hn is a predictable process. So by the theorem that we saw in the last class, we know that h, x, n, this new process, is also a martingale. Okay, so let's recap what we did. So we started with a martingale. We decided that this strategy to buy low and sell high seemed like a smart strategy to make money. So we defined it rigorously, first through these stopping times and then defining H properly. We showed that H is a predictable process, so we are not trying to read the future before we decide to buy or sell X. And we obtained, by the last class theorem, that HX is a martingale. Now, what we're going to prove is a theorem that uses this fact in its proof. So the theorem has to do with the random variable u, called the Upcrossing. So remember that this class is called Upcrossing Probabilities. So let's define the Upcrossing un. Un is simply the maximum k such that sk is smaller or equal to n. What does that mean? It's the number of times that we crossed the curve from bottom to top until time n. So if we look back into our martingale here, and this is time n, this is time n, then we see that S0 is smaller than n, good. S1 is smaller than n, good. But S2, probably is here, I don't know, is bigger than n. So it doesn't count. Here we know that un is equal to 1. It's the maximum Si which is smaller than n. Let's go back to the definition here. It's the supremum in k such that sk is smaller or equal to n. And the intuition behind the definition is the number of times that we crossed from A to B up here and here. See? Minus 1. So it's 0, 1. Okay. Actually, maybe we should probably sum 1 here to get really the number of times we go up. So in that case, it was going to be u equals 2. Okay, so what the Upcrossing probabilities theorem tells us. So suppose that xm is a sub-martingale, then B minus A. So B and A are as we defined above. Of course, A has to be smaller than B for what we're talking. B minus A times the expected number of upcrossings of times we go from B to A is bounded by the expectation of xn minus A positive part minus the expectation of x0 minus A positive part. So don't worry much about the right hand side for now. What is interesting is that we are bounding the expected number of times we go up. So first, the intuition, right? We know that H that we defined above is a strategy that tries to make money every time we do an up crossing like this. So the fact that we cannot make money in a martingale should tell us that we cannot make money, we cannot make many up crossings. But okay, we are starting with a sub martingale. And for example, xm equals m is a sub martingale. It's always going up. We are making money. So how do we explain this? Actually, what I'm saying is the number of up crossings cannot be better than essentially just buy and forget. This is like buy, forget the initial money you spent, right? Just buy and forget. Just almost like expectation of xn, so to say. So we cannot make more up crossings than what we would do of money by just buying and forget divided by b minus a. So this is the intuition behind the theorem, and the exact form that we wrote here is the form that's most useful. So it's going to become clear later why we decided to write it exactly like this. So let's go straight to the proof. So we define another process, ym, which is just going to be a plus xm minus a positive part. The reason we do this is first we are trying to center things around a, so to say, but we also want to keep the property of being a sub-martingale. So remember x being a sub-martingale, and this function here, positive part, is a convex non-decreasing function. So y is also a sub-martingale by a theorem we saw before. So now we have this auxiliary sub-martingale, and we have the h that we defined above, and hy is also going to be a sub-martingale. Applying an integral with respect to a predictable process to a sub-martingale cannot change the fact that it's a sub-martingale. Now we can rewrite ym minus y0 in two terms. So whenever we are trying to do these strategies of showing that something cannot make money, actually what we do is we write the difference in, this is the strategy that doesn't sell or anything, just buy in the beginning and stay with the y forever. And this is a strategy that keeps trying to buy and sell, right? And the way we can rewrite this left-hand side is just summing hk, hy with ky, where k is another strategy with just 1 minus h. So what we're saying here is, okay, this is the strategy of someone who buys y and never changes the portfolio. This is the strategy of someone who buys y only on those intervals between low and high. And this is someone that, is doing the opposite. Whenever you think there is a bad strategy to buy, they buy. So this is our complete opposite strategy. It buys high and sells low. And we know that all of these are martingales. So KY is also a sub-martingale. Which is strange, right? We specifically designed this strategy to make money. We know that it's not going to make money. And this opposite strategy that's supposed to be the strategy that loses money also makes money. Nobody can make a bad strategy in a sub-martingale. Now, if we take expectations on both sides here, we're going to get here the expectation of the integral y, hy plus the expectation of the integral ky. And by the fact that these are sub-martingales, we can bound this. We can replace m by anything smaller in any of these integrals, but we're going to do it only with the right one. So this is bigger than this by the fact that k is a submartingale. Okay, so this thing here, every stochastic integral at time 0 is exactly equal to 0. Okay, if you remember the definition of the integral of a martingale, at time 0 it's exactly 0. So what we are obtaining here is that the expectation of h, y, m is smaller or equal than the expectation of ym minus y0. Okay, now we have done some calculations about our strategy our strategy h applied on y, but we have not talked yet about the upcrossing probabilities. The upcrossing number is interesting because it lower bounds the profit of our strategy. So if you go back to that graph there, if our stocks cross these lines u times, from here to here, if it crosses from bottom to top 1, 2, 3 times, it means that this strategy made at least 3 times B minus A profit. So here we can put lower bound the expected profit by B minus A, A, the expected number of upcrossings until time m. And the reason this is true is because for every configuration, h, y, m is at least b minus a u m. So if this is true for every configuration, we can reflect this in the expectation. Okay, so now we have a bound on the expected number of upcrossings in terms of the simple-minded strategy to not buy or not sell any time. In the end, we get the desired bound that the b minus a expectation of um is bounded by. So let's just split this sum here and use the definition of y. This is xm minus a, positive part, plus a. Here I'm gonna get some space here, minus the expectation of x0 minus a, positive part, minus a. These two terms cancel and we get the result. So let's go back to the result and see that it's indeed what we got. The expected number of upcrossings times the money you win in each upcrossing is bounded by xn minus a positive part minus x0 minus a positive part. So this finished the upcrossing probabilities estimate. And the next class, we're going to use this to show very interesting theorem about martingales, a quite surprising theorem. That's actually the application we were after from the beginning.